Hello class, this is Ms. Jacoy, and we are looking at the basics of kinematic equations. So, first off, we're going to look at what do the variables mean. So there's some variables that you need to know in kinematics, and we're going to go over each one. And then what are the main equations? There are some main equations in kinematics, and you do need to get very good at understanding when and what they are for. Alright, so to start with, we have some variables that we need to know. So, x in physics is our position. So, then you're going to start, before I forget to mention, with each one of these there is a unit attached to it, a way that we measure it, and I'll come back to that. V is velocity. So velocity, so you have a position. Your position is essentially where you are in space. You could be 1 meter away from your friend. You could be 5 meters behind your house, 10 meters away from your car. It's where you are in relation to something else. Velocity, however, is how fast that position is changing. So by definition, it's the change in position over a period of time. So you have to have both position and time for this to work. So for example, if you are 10 meters away from your car, your velocity would be, so if you went from your 10 meters away from your car to your car, you changed 10 meters in position. And then let's say it took you 5 seconds to do it, so your velocity would be 10 over 5, or 2 meters per second. A is acceleration. So acceleration is like velocity, and that it's another derivative of. So acceleration is the change in velocity over time. So let's say you're speeding up or slowing down, whether or not it's acceleration or deceleration. Deceleration is just negative acceleration. We call it both. So it's your change in velocity over a period of time. And T stands for time. Hopefully you know what time is. So going back to our units. So your units for position, you might have heard me mentioning them, are in meters. Sure, we use feet here, but pretty much the rest of the world uses meters. It's the standard scientific unit for measurement of position and distance. V is velocity, so remember it's a change in position, which is meters, over time, and we measure time in seconds. Now, acceleration is we have velocity over time, so velocity was already meters over seconds, so now we have meters over seconds squared, because we added an extra time unit in there, and time, if you haven't picked up yet, is measured in seconds. Alright, so these are still just position, velocity, and acceleration, but that little O at the bottom there means initial, and it's said as naught. So x naught, v naught, a naught means x initial, v initial, a initial. So just know anytime there's that little naught sign there, it's the initial, or you can think of it as the starting value, or the starting position, starting velocity, or starting acceleration. Another notation, this AVE just means average. So the average velocity or the average acceleration. Alright, so now we're going to go up to this upper right hand corner where we have the Greek letter delta. So delta stands for change. So for example, if we wanted to talk about change in x, we would have the final x, subtract the initial x, or x naught. If we want to figure out the change in velocity, we'd have the final velocity minus the initial velocity, or v naught. If you have a change in mood, you would have your final mood minus your initial mood. We'll get your change in mood. If you have a change of heart, you would have your final heart minus your initial heart. So it's, if the main thing with delta, it's the final minus the initial. Alright, and these are your three main equations for, oops, not what I wanted to do. These are your three main equations. And then the next two aren't necessarily equations. You can think of them as more of a, how do you say, they're more of a definition of the average velocity and the average acceleration. Alright, so we're looking here at the first kinematic equation, and all equations are essentially a set sentence written in a slightly different language. So remember, x is just our position. So we can think of this as where you are. And the equals is. So where you are is x naught, the initial position, where you started, plus, and your velocity times how long you ran for. So this is your initial velocity times time, plus, we can think of it as and, half of your acceleration times time squared. So hopefully this makes a bit of sense in the idea that where you are is dependent on where you started, how fast you were going and how long you went that fast for, and then how much you accelerated or decelerated for how much you accelerated or decelerated for. So to put some of that into action, let's say we got a little guy, and this little guy has an initial velocity of 3 meters per second, a positive acceleration, so he's speeding up at 0.5 meters per second. Oops, squared, almost messed up my units. And we want to know where he's at t equals 3 seconds. So you would just use your equation. So we want to know the final position is equal to where we started plus initial velocity plus 1/2 acceleration times squared. So we have our v naught, we have our a, we have our t is 3. The only one it looks like we're missing, because this one we're trying to find, is our x naught, or our initial position. Well, if you think about it, your initial position is not necessarily very important. There's nothing it's relative to. We could just say we're at 0, because sure, why not? We're at 0. However far we go is however far from where we started. So you can go ahead and let this just be 0, so it essentially cancels out. So you'd have x, your position, is equal to 3, your velocity, times your 3 seconds, your time, plus your 1/2 times your 0.5 meters per second squared acceleration, times your 3 seconds for time. Do not forget to square that time. That is a very common mistake not to bring that squared down, as I almost just committed. Alright, then you're going to solve this. And if you want some help with the units, notice your seconds here cancel, so this would be 3 times 3 is 9, your units are meters, plus 1/2 times 0.5 times 3. Notice this second gets squared, and this 3 gets squared, so we're going to have 9 seconds squared here. You have these 2 seconds squared out, we're going to end up with meters. And then it would be 9 times 0.5 times 1/2, which gets you 2.25. Add this to 9, and you'll get 11.25 meters. Alright, so the next equation is velocity is equal to initial velocity squared, or velocity squared is equal to initial velocity squared plus 2a. And it's either written one of 2 ways, either delta x, which I tend to prefer because it's shorter, or just to write the whole thing out again, 2ax minus x initial, because remember that's what delta x means. So remember, this is how fast you are in the end. This is how fast in the beginning your acceleration times your change in position. Alright, so let's imagine a new person. So we got this girl. Her initial velocity is 2 meters per second. She's starting at the 0 meter mark. And her acceleration is 1.2 meters per second squared. And we want to figure out what her new velocity is. So we'd set it up as velocity squared is equal to v naught squared plus 2a delta x. Still don't know our v squared, but we do know our v naught is 2 squared, plus 2 times our 1.2 meters per second squared, times our change of position. That would be 10 minus 0, which is still just 10. So our 2 squared would give us 4, plus 2 times 10 times 1.2. Or 24. And that will give us 28 is equal to v squared, and then v is equal to the square root of 28. And if you plug that in your calculator, which is approximately 5.3 meters per second, because this is velocity. Alright, so the last equation is velocity equals initial velocity plus acceleration times time. Again, hopefully this one makes some sense, where this is your final velocity, which is a result of your initial velocity plus your acceleration times the amount of time you accelerated for. Alright, so looking to solve that, we've got person running again. Their initial velocity is 4 meters per second. Their acceleration is negative 1 meters per second squared. So if you want to think about that, they're slowing down. They are decelerating since there's a negative acceleration. So we want to know how fast they're going. Notice I didn't bother putting any distances because we don't care about distance. Distance doesn't depend or matter to how fast you're going, as long as we know the initial velocity and the acceleration. So we can plug into our equation, where this is 4 meters for our initial velocity, plus, remember, this is a negative 1 meters per second squared, and I forgot to put the time, but the time we are looking for is 3 seconds. So 3 seconds. Hopefully you know that gets you a negative 3 meters per second. 4 minus 3 gives you 1 meters per second. So after 3 seconds, they have slowed down considerably and are only going a final velocity of 1 meter per second. So I'll be releasing more videos on how to solve these equations later, but I just wanted to have a quick basic run through of each one and the variables in them. See you in the next video.